So our next speaker is Kamana Porwal. She is a faculty member at IIT Delhi now. So she was also a student of IISc. So she finished her PhD in 2014, and then she was a postdoc at Louisiana State University. And she was also in CAM and IIT Gandhinagar for a brief period. Her main interest is analyzing finite element methods for nonlinear PDE. And today she is going to talk about pointwise adaptive quadratic FEM for elliptic optical problem. Over to you, Kam.
Yeah, thank you. Thank you, Professor Datti, for the kind introduction. And I'll just share my screen and please confirm it.
Sure. Yes, your screen is visible now.
I think she is muted. I think we can't hear.
We can't see the screen also.
Yeah, now it has vanished. It has vanished.
Let me.
I think from her side, she has to do something.
Okay, let me.
Now it's coming.
Is it fine now?
No, we are not able to see your screen.
Okay, let me just share again.
Yeah. Yeah, now we can see the screen.
Okay, and am I audible?
Yeah, we can hear you.
All right, so let me start again. So in the brief outline of my talk, so here's the brief outline of my talk. So I'll start with presenting the continuous obstacle problem, and then we will see the quadratic finite element approximation for it. Followed by that, I will discuss the pointwise a posteriori error estimates for the underlying finite element method. And finally, I will conclude with presenting some numerical results. So the variational formulation of obstacle problem is to find the solution of this variational inequality in the set K, where the set K is a closed convex subset of H1 naught omega, whose functions are constant to lie above the obstacle chi. Okay, so chi here is a given function which we have assumed that which is Helder continuous, and it satisfies this compatibility condition across the boundary of the domain. The bilinear form A here is given by this. So we can observe that this bilinear form A is continuous and cohesive over H1 naught omega, and the set K is non-empty, closed, and convex. So by using the result of Stampecchia, this continuous problem has a unique solution. So here is the strong form of the obstacle problem. So if the solution U is sufficiently regular, then it satisfies this Poisson equation in the non-contact region, and it coincides with the obstacle in the contact region. And across the interface gamma, we have these transmission conditions. So gamma here is the boundary of the contact set. That is a set where the solution touches the obstacle. So this problem basically models the vertical displacement of an object which is constrained to lie above the obstacle chi and which is subject to a vertical force F. Okay, and note that not just the solution U here, but the location of this interface gamma is also unknown. So this problem falls into the category of the free boundary problem, and this interface gamma is known as the free boundary. So numerical analysis of these free boundary problems are very important because they have various applications in engineering, physics, and mathematical finance, to mention a few. Now we introduce this functional sigma, which is basically the residual of the solution U with respect to the variational formulation, and we extract these properties for this functional sigma. So first property is directly obtained by the definition of the sigma and the continuous variational inequality. And then we choose the test function V here as U plus phi, where phi is a non-negative H1 naught omega function, to obtain this property of the sigma. So it basically says that the sigma is non-positive. And we can also prove that the support of the sigma is contained in the contact set. Coming on to the finite element methods, let me first introduce some notations. So TOH denotes the regular triangulation of the domain omega, and we denote the continuous space by V, which is a space H1 naught omega for our case, and we denote the discrete space by VH. So note that we are concerned about the conforming finite element method. So the discrete space VH is going to be a subspace of the continuous space V. And in particular, we are interested in the quadratic finite element method. So the space VH is the space of the continuous piecewise quadratic finite element functions, which vanishes on the boundary of the domain. Then the set KH, which is a discrete analog of the continuous set K, is the set of all those functions of VH which satisfy these constraints. So here, note that the constraints are being imposed at all the midpoints of the triangulation, midpoints of the edges of the triangulation. So then the finite element approximation of the obstacle problem is to find the solution of this variational inequality in the discrete set KH. And we observe that this discrete set KH is non-empty, closed, and convex, and the bilinear form A is bounded and cohesive over VH. Hence, this discrete problem also admits a unique solution. Now, let me quickly explain that what we are intended to do further in this talk. So we are interested in the a posteriori error analysis, basically the pointwise a posteriori error analysis. So that is what we are interested. We're interested in deriving this quantity eta. So this quantity eta is a computable quantity, and it depends on the discrete solution UX and the given data. And we aim to show that this quantity eta provides an upper bound of the error also and lower bound of the error up to some higher order terms. Now these estimates, okay, so this quantity eta is called the a posteriori error estimator, and this eta being the upper bound of the error is called the reliability of the error estimator, and this eta being the lower bound of the error is called the efficiency of the estimator. Now these estimates ensures that eta will have the same convergence rate as of the actual error. And also this estimator eta can be computed locally over each element. So if the eta is large in some region, this means that the solution, this means that the error is going to be large in those regions, and hence the mesh can be refined there to get a better accuracy of the solution. And that will also lead to the adaptive mass refinement. Now, in the last 2 decades, there has been a lot of work on the analysis of adaptive finite element method for the obstacle problem. And I refer some of these works here. So these first 3 works are focused on analyzing the linear adaptive finite element method for the obstacle problem. But the norm under consideration here is the energy norm. And these next 3 works, they basically discuss the adaptive finite element method, and the finite elements are the quadratic finite elements here, and the a posteriori estimates are derived in the energy norm. So the literature towards the pointwise a posteriori estimates of finite element methods for the obstacle problem is very limited. So I refer to these 2 works here, where the pointwise a posteriori analysis of conforming linear finite element method is being derived for the obstacle problem. So this talk is based on this work, where we have derived the pointwise a posteriori error analysis of quadratic finite element method for the obstacle problem. So now to define the error estimator, I'm going to require some more notions and definitions. So let me introduce them first. So psi p here denotes the nodal basis function of the discrete space VH. Now the discrete space VH is a quadratic finite element space. So P is going to vary over the interior vertices and the midpoints of the edges. And then we use this basis functions associated to the midpoints of the edges to define this space ZH. So with the help of this ZH, we can write the discrete space VH as the direct sum of ZH and ZHC, where this ZHC is defined in this way. So here this ZHC is basically the orthogonal complement of ZH in VH with respect to certain inner product. And we denote the Kruser-Raviat finite element space YVNC. So it is a space of piecewise linear functions which are continuous at the midpoints of the edges. Now, analogous to the continuous Lagrange multiplier sigma, we need to define the discrete Lagrange multiplier associated with the discrete problem, and we have defined it in this way. So here this H inner product is defined in this way, and it is the lumped mass inner product what Professor Vedart Homi was introduced in his last lecture, in his lecture which he gave yesterday. And pi h here, pi h here is the operator which connects the discrete space VH to the non-conforming finite element space VNC, and it is defined in this way. And we can observe that this pi h is both 1, 1 and on 2, hence its inverse exists, and it is given by this. So phi here are the basis, so phi denotes the basis function for the non-conforming finite element space VNC. And we have the standard approximation properties for pi h and pi h inverse both. Now the discrete Lagrange multiplier sigma h satisfies this sign property, which is crucially used in the analysis. So if we denote the QH as the L2 projection operator onto the space of the piecewise constant functions, then we have that the QH sigma h is non-positive in the whole domain. Now let's see how do we obtain this sign property of the QH sigma h. So we take the test function VH as UH plus psi m, where psi m is the basis function associated with the midpoint of the A's, and we use the discrete variation inequality to obtain this relation. Now we take the test function VH as pi h inverse psi m in the definition of the sigma h, and then we use this relation to obtain that the sigma h at all the midpoints of the edges is going to be non-positive. And finally, we use this integration rule, which is exact for the quadratic polynomial, to conclude that the integral of the sigma h over the element is going to be non-positive, and which basically gives us that QH sigma h has this sign. So now in the main result, we have obtained that the error in the solution and the error in the Lagrange multiplier can be controlled by the error estimator eta h, where this error estimator eta h is the sum of these contributions. And these contributions are given by this. So eta 1 here is the volume residual, and eta 2 is the jump residual, and eta 3 measures, so it is basically a consistency error, which is induced by taking the QH sigma h in the residual functional in place of the sigma h. And eta 4 and eta 5, they are arising because of the inconsistency of the obstacle at the continuous and the discrete level. That is, we don't have chi equals to chi h. Now I will briefly discuss the steps or the main ideas of obtaining the reliability estimate. So first we construct these barrier functions, u upper star and the u lower star, and we prove that the solution u can be controlled. Solution u is basically bounded above by u upper star, and it is bounded below by u lower star. Now look at these barrier functions u upper star and lower star. So they are constructed by using the discrete solution UH and a corrector function W, which is basically the reach representation of the residual functional GH, which is defined in this way. And the rest of the term in the these barrier functions are just the computable quantities. So now let's proceed to show that U can be bounded above and below by these barrier functions. So first we show that U is bounded above by U upper star. So idea here is that I'm going to take the positive part of U minus U star, and I'm going to show that that is 0. So if the positive part of U minus U star is 0, then basically I'm going to have that U minus U star is non-positive. Okay, so we define the function V as the positive part of U minus U star, and our claim is that this function vanishes in the in omega. So let's make some observation about this function V here. So we have that U is in H1 omega, and U upper star is also in H1 omega. So, and we know that the positive part of an H1 function is again in H1 omega. So V is in H1 omega. Okay. And secondly, this function V also vanishes on the boundary of the domain, because if we consider U minus U star, we just use the definition of the U star here, and we know that U, UH, and W, they all are 0 on the boundary. So U minus U star is less than equal to 0 on the boundary. Thereby, the function V is going to be 0 on the boundary of the domain. So in fact, the function V is in H1 naught omega. And the Poincare inequality can be applied for the function V. So it suffices to show that the L2 norm of the gradient V is 0, because that will give us that the L2 norm of the V is 0, and then from there I will be able to conclude that V is 0 in the domain. Okay, so I consider the square of the L2 norm of the gradient V, and I simply use the definition of the V. So 1V, I'm keeping it as it is, and for 1V, I use its definition, keeping in mind that U minus the positive part of U minus U star and negative part of U minus U star, they will have a disjoint support. So using that, we obtain this relation, and then we use the definition of the corrector function W to obtain this term. And finally, we use the definition of the residual functional GH to obtain this. Now, from this step to this step, I'm simply using that we have a sign of the QH sigma h. So we have proved that QH sigma h is non-positive. So, and V is a positive function. So using that, we obtain that this term is bounded below by this term. Now, finally, we arrived at this term by using the fact that the Lagrange multiplier sigma can be represented as a Radon measure. So we obtain this term. So we are done if we show that this integral is non-positive, In fact, we obtained that this integral is 0. And for that, it suffices to realize that the support of the V and the support of the sigma, they are going to be disjoint. So let's see that how do we obtain this? So if we take any point X in the domain where V is strictly positive, then by using the definition of the V, we have that U is strictly greater than U star there, and U star is this function. Now note that W plus norm W, this is always a positive function. Okay, so this expression is bounded below by this function, and this is further bounded below by the obstacle chi. So we have that the support of the V is contained in the non-context set, and we already know that the support of sigma is contained in the context set. Hence, the two supports are disjoint, and we are going to the desired result. That is, we have that U is bounded above by Q upper star. So in the same spirit, we now try to show that U can be bounded below by U lower star. So again, we define this function V as the positive part of the U star minus U. And we will show that this function V is 0 in the domain omega. So once we show that, then we will have that U star minus U is going to be less than equal to 0. So again, U star and U lower star and U, they both are H1 function. So V is H1 function. And we observe that it vanishes on the boundary of the domain because U star minus U is basically this expression. And here, these three terms, they are going to be, so W minus norm W is a negative term, and this is also a negative term. And we know that UH and U both are 0 on the boundary. So basically, we have that U star minus U is less than equal to 0 on the boundary. And thus, we have that V is equal to 0 on the boundary. So V becomes a H1 naught omega function, that is V is in the space H1 naught omega. So the Poincare inequality holds. And again, we just have to show that the L2 norm of the gradient of the V is 0 to obtain that we have the sign of U lower star minus U. So let's focus on the L square of the L2 norm of the gradient of V. So we again use the definition of V by keeping one V as it is. And then we use the definition of the corrector function to obtain this. And then we use the definition of the residual function to obtain this. So this term is very similar. I mean, it's similar to the one which we have in the previous case. Only difference here is the minus sign. So in the previous case, we had QHEH minus sigma, and now we have sigma minus QHEH. So now we use the sign property of the sigma. So we know that sigma is non-positive. So we obtain that this term is bounded below by this term. And our claim is that this term is 0. That the integral of QH sigma into V over the domain omega is 0. And how do we realize this? So we prove it in two steps. So firstly, we prove that if there exists a point X in the interior of T, then the QH sigma is going, where the V is strictly positive, then the QH sigma H is going to be 0 on that element. And we prove it by contradiction. If we have a point X in the element T where Vx is strictly positive and QH sigma H is strictly less than 0, then by using the definition of V, we can obtain that U is strictly less than chi at the point X, but which is a contradiction because U is greater than equal to chi X. So now let's consider this integral. The integral of QH sigma H into V over the element T. So if V is identically equal to 0 on the element T, then of course, this integral is 0. If not, then there will exist a point in the interior of T where V will be strictly positive. But we have proved in this step 1 that QH sigma H is going to be 0 in that case. So basically, we obtain that this integral is 0. And finally, we conclude that the integral of QH sigma H V over the domain omega, this is 0 because it can be written as the sum of these integrals. So here the integral is over the element and each of these terms vanishes. So thus we obtain that the u lower star is the lower bound, provides the lower bound of the solution u. So using this last lemma, what we have is that u minus UH. So I'm just taking the solution u, discrete solution u to the, so we have u is greater than u upper star. So I'm taking the discrete solution UH to the right hand side. And we have proved that u is greater than equal to u lower star. So again, I'm moving a UH to the other side. So basically we obtain that u minus UH is bounded below by these terms, and it is bounded above by these terms. So combining these, we obtain that the pointwise error in the solution can be controlled by these terms. So here, these two terms are the part of the estimator. And so what remains to prove here is to obtain the pointwise estimate for the corrector function W. So using the Green's function estimate, we obtain that the elementary norm of this corrector function W can be controlled by the error estimator terms in this way. And finally, combining both these results, we obtain this reliability estimate. So I'm skipping the details here because those are more technical and it will require more time. So now we have this reliability estimates for the error in the solution. To obtain the reliability estimate for the error in the Lagrange multipliers, if we consider this term, so if we simply add QH sigma H, because we have defined the residual functional is defined using the QH sigma H, and then we use the definition of the GH to obtain this. So then we can conclude this reliability estimate by simply using the approximation properties of the QH and Sobolev inequality and this estimate for the residual functional. And next we have proved that each of these estimator terms are locally efficient. That is, they can be controlled by the local error. And the proof of these estimates requires this, I mean, it uses the standard bubble function techniques. Hence, I'm skipping the details here. And I would like to remark here that because of the quadratic nature of the discrete solution, we could not succeed in proving the efficiency of this term. So this term is of higher order, but we could not prove that this term is efficient theoretically. But numerically, this term turns out to be efficient. Now I will present some the results of some numerical experiments. So for the adaptive mass refinement, we are considering this 4-step algorithm: solve, estimate, mark, and refine. So in the step solve, we solve the discrete problem, that is a discrete variational inequality, using the primal dual active set method to obtain the discrete solution UH. And then in the estimate, we compute the error estimator eta H over each of the element. And we use that to mark the angles for the mark the elements for the refinement using the maximum marking strategy. And finally, we use the newest vertex bisection algorithm to refine the marked elements. So this process will yield the adaptive mass. So now I'm going to present the numerical test results for 2 examples. So in this example, we consider this square domain, and the obstacle chi is 0 here, and the exact solution and the source function is given by this. Then this figure shows the behavior of the error and the estimator with the increasing number of degrees of freedom. So this black line is the optimal rate, and this blue line is the error, and this red line shows the behavior of the estimator as we increase the increase the degrees of freedom. So we can observe that both error and estimator, they are converging with the optimal rate. And also the estimator is always an upper bound of the error, which ensures the reliability of the error estimator. Efficiency indices, which are basically the ratio of estimator and error, they are depicted in this figure, and they shows the efficiency of the error estimator. And this figure shows the adaptive mass refinement at certain level. And we observe that there's a more refinement along the free boundary, because the solution is 0 when we have R is strictly less than 1. So the free boundary is going to be R is equal to 1. Okay, so we observe that the mass is refined more in this region, because the solution will have the large jump in the gradients in this region. Now we consider this another example where we have considered the non-convex domain. So here the omega is basically a L-shaped domain. And we have this set of data. So we can note that the solution U is similar in the sense that the gradient of U will have the singularity near the origin. So for this example as well, we obtain that the error and estimator both converges with the optimal rate. And also the estimator is reliable because it is always an upper bound of the error. And the efficiency of the estimator is shown in this figure by using these efficiency indices. And here is the adaptive mass refinement. So we have reported it at the certain intermediate level. So we observe that there's a more refinement near the origin because the solution is having singularity in the gradients near the origin and along the free boundary. And this refinement is because if you see the function f itself, so that is like a Dirac function. So this figure basically illustrates that the error estimator eta h captures the singular behavior of the discrete solution quite well. And with that, I come to the end of my talk. So in this talk, we have discussed the pointwise a posteriori error estimates of quadratic finite element methods for the obstacle problem. And the main tools for the analysis was the proper construction of the Verrier functions, discrete Lagrange multiplier, and the estimates for the corrective function. And we presented the numerical results illustrating the convergence behavior of the a posteriori error estimator. Here are some relevant references. And this talk is based on this work, which is accepted recently. So with that, I will end here.